In earlier lessons, we learned about the uncertainty principle, which is a consequence of wave-particle duality. Location and momentum, which according to the uncertainty principle cannot be precisely determined at the same time, are examples of what are called complementary variables. In this lesson, we will see that the uncertainty relationship between complementary variables arise naturally from the first postulates of quantum mechanics that we have just covered. So far, we have explored the first four postulates of quantum mechanics. Postulate 1 says that there is a function that has all accessible information about the system. Postulate 2 says that there is a Hermitian operator that corresponds to every dynamical property of the system. We have also learned the rules for constructing these operators. Then we learned postulate 3, which tells us that the only possible outcomes if we try to measure a property are the eigenvalues of the operator that corresponds to that property. In our postulate 4, we actually made two assumptions, which may be taken as separate postulates, as you may see in some textbooks. First, we assume that an operator that corresponds to a property of the system has a complete set of orthonormal eigenfunctions. This meant that the state function psi can be written as a linear combination of the eigenfunctions. Second, we assume that the probability of obtaining eigenvalue a sub I if we measure property A is equal to the square of the absolute value of coefficient c sub I for eigenfunction f sub I. This meant that the expectation value of property A can be obtained by applying operator A on psi, multiplying it by the complex conjugate of psi, and integrating over all space. We can write this integral this way using the Dirac bracket notation. We put psi in the bra and ket and put operator A in between. In typical textbooks, the formula for expectation value is given as the assumption, and from this assumption, we can infer that the square of the coefficients are the probabilities, since the expectation value can then be shown to be a weighted sum of the eigenvalues, with the weights being equal to the square of the coefficients. Whether or not two properties can be precisely determined at the same time depends on the commutator of their corresponding operators. So let's first talk about commutators. If we write operators A and B separated by a comma inside a pair of square brackets, we read it as the commutator of A and B. It's just another operator, and it is defined as the product operator A hat B hat minus product operator B hat A hat. Therefore, if you apply the commutator of A and B on a function, this is what you do. Apply B hat first, then A hat. Then reverse the order of the operators. Then take the difference of the results. Let's look at an example. What is the commutator of the location and momentum operators x hat and p sub x hat? We first apply the operator product x hat p sub x hat on arbitrary function f. Next, we reverse the order. Then we take the difference. Let's look at the first term. We apply the rightmost operator first. P sub x hat applied on f is h bar over I times the derivative of f with respect to x. Then we apply the next operator. X hat is just a multiplicative operator. So x hat applied on the resulting function is just x times h bar over I times the derivative of f with respect to x. Multiplication is commutative, so we can switch h bar over I and x. Now let's do the second term. We apply the rightmost operator first. X hat applied on f is just x times f, since x hat is just a multiplicative operator. Next, we apply p sub x hat on the resulting function, which is x times f. This gives us h bar over I times the derivative of the product xf with respect to x. The derivative of product is equal to the first factor times the derivative of the second factor plus the second factor times the derivative of the first factor. So here's what we have so far. You can see that for the right-hand side, we can factor out h bar over I. This gives us h bar over I times x times the derivative of f with respect to x minus x times the derivative of f with respect to x minus f times the derivative of x with respect to x. We can see that these two terms are the same and so they cancel out. Our expression simplifies to h bar over I times negative f times the derivative of x with respect to x. The derivative of x with respect to x is just equal to 1. So our expression further simplifies to just negative h bar over I times f. In other words, the net effect of the commutator of x and p sub x on an arbitrary function f is to simply multiply f by negative h bar over I. If the operators for two properties commute, then it means that the order you apply them on a function does not matter. In other words, if operators a and b commute, we can say that applying the commutator of a and b on an arbitrary function f gives us what? It gives us 0. We can also say that their commutator is a null operator. It just multiplies the function it is applied to by 0. It also means that it is possible to precisely determine a and b at the same time. But why? The reason is that we can prove that the two operators will have in common between them a complete set of eigenfunctions. Note that we're not saying that each and every function of one is an eigenfunction of the other. In the Venn diagram shown here, if red circle represents the set of all the eigenfunctions of operator A, and the blue circle represents the set of all the eigenfunctions of operator B, then within the purple region where the two circles intersect, we can find a complete set. Note that when we say a complete set, we do not necessarily mean all eigenfunctions. This will become clearer when we look at specific examples later. So what if the two operators have common eigenfunctions? Well, let's go back to postulate 4. We said that psi can be written as a linear combination of the eigenfunctions of the operators for any of its properties. So it is possible for psi to be equal to just one of the eigenfunctions of operator A. That means a hat applied on psi gives back a constant, shown here as a lowercase a, times psi. This means that a measurement of property A will give exactly the eigenvalue A. If it's possible for that eigenfunction of A to be an eigenfunction of B as well, then B hat applied on psi gives back a constant, shown here as lowercase b, times psi. This means that the measurement of property B will also give us an exact result, the eigenvalue B. What if the operators do not commute? Then that means they do not have a common set of eigenfunctions, and in general, they cannot be simultaneously determined exactly. It can be shown that the product of the uncertainties will at least be 1/2 times the absolute value of the integral shown here. To evaluate the integral, we apply the commutator on the wave function, then multiply by the complex conjugate of the wave function, then integrate over all space. In Dirac bracket notation, the expression can be written this way. We write psi inside the bra and the ket, then put the commutator in between. Some textbooks consider this a postulate, but it shouldn't be since it can actually be derived from our postulate number 4. Example. Let's derive the expression for delta x times delta px. Delta x times delta px is at least equal to 1/2 times the integral shown here in Dirac bracket notation. Note that psi is both in the bra and the ket, and the commutator of x and p sub x is in the middle. We have previously shown that the commutator of x and p sub x is negative h bar over I. We can pull negative h bar over I out of the integral since it's just a constant. The absolute value of negative h bar is h bar, and the absolute value of I is 1. So the absolute value of h bar over I is just h bar. Since psi is normalized, the integral of psi star psi over all space is equal to 1. Therefore, the product of the uncertainties is at least h bar over 2. In our expression for the uncertainty principle, the uncertainty refers to the standard deviation and can be calculated using this formula. We take the expectation value of a squared, subtract from it the square of the expectation value of a. This difference is called the variance. The standard deviation is just the square root of the variance. Remember that you can calculate the expectation value of a by evaluating the integral shown here in direct bracket notation. Psi goes into both the bra and the ket, and a hat goes in the middle. Similarly, you can calculate the expectation value of a squared by putting the a hat squared in the middle instead. Remember, a hat squared means a hat is applied twice. Since operator a is Hermitian, you should be able to show that the expectation value of a squared is also equal to this integral, where a hat psi is inside both the bra and the